This is the first lecture on the topic of conjoint measurement, and it will be concerned with additive representations. The subject of conjoint measurement is a fairly recent one as a formal measurement theoretical area. However, the motivation, some of the motivation for the work is really quite as old as the motivation from physics that led to the theory of extensive measurement. In physics, one has, at least in classical physics, a structure of units that relate different dimensions, and one finds frequently laws of physics that are of the general form: one variable z is the product of two other variables. Let me give a couple of examples. The expression force equals mass times acceleration is of this character, or that kinetic energy is a half mass velocity squared is of this character. A multiplicative relationship, and sometimes it's multiplicative in powers of a variable. So that more generally I can write this as z equals x to some power alpha, y to some power beta. Or if I take logarithms, this becomes the log of z is alpha log x plus beta log y, so that it is additive in the logarithms. However, the physicists make the convention that when they're dealing with a scale that is resulting from manipulation of two other scales, they will write that relationship multiplicatively rather than additively, and within a scale the extensive structure is written additively. And recall that we pointed out in the lectures on extensive measurement that it's arbitrary whether one is going to use a multiplicative or additive representation of those structures. So throughout physics, one sees a lot of structures of this general character. And in fact, one interesting problem that we'll go into in the lectures on dimensional analysis is exactly how you relate this kind of a structure to the extensive structures that have been developed for certain of the measures, mass, and so on. These arise often in situations where one or maybe two of the variables involved are extensively measurable, but not all of them are. A good example, for instance, is the relationship of mass, density, and volume. Volume and mass are extensive measures, but density itself is not. And in fact, in general, in physics, one defines density as the ratio of mass to volume. In economics, particularly in the 19th century, there was a good deal of discussion of whether the utility of a commodity bundle was additive in the several commodities. And while that assumption was ultimately abandoned, and much of classical economics essentially rested only on ordinal properties of utility, from time to time the issue of additivity has arisen, and one is interested in understanding the conditions under which that could occur. In psychology, my own field, there were several motivations for studying conjoint structures. One very important one is that by and large in psychology we have been unable to find concatenation operations that would permit us to develop scales of measurement in a fashion analogous to physics. One of the problems, well, there are two kinds of problems about concatenation operations. One is sometimes one can find an operation that appears to be a concatenation operation, but that the axioms of extensive measurement don't seem to be satisfied. That would lead to developments in trying to generalize the theory of extensive measurements, and we will be talking about that in another lecture. In other situations, it's seems to be very difficult to figure out what is a suitable concatenation operation. On the other hand, it is frequently found that you're in what is called a factorial situation. That is, the variable in question, the dependent variable, is manipulated by two or more independent variables. A simple example, for instance, is that the loudness of a sound is affected both by the intensity and the frequency of the sound. It is that dependence on frequency, the dependence of loudness on frequency, that leads hi-fi designers to put loudness control corrections in the design, because of the sound at high frequencies and low frequencies varies depending upon the intensity that it is presented. There's an interaction there. There are many, many situations in psychology where factorial designs play a role. And you see it essentially in the form of studies of various kinds of trade-offs. For instance, in animal work, the trade-off between the amount of a reward and the delay of a reward. In particular, in a lot of the statistical analysis used in psychology, additive models are proposed, and they play a very important role in the analysis of variance. So psychology is fairly strongly motivated to try and study situations in which the structure is factorial in character. I should also point out that in the period of the 1920s, there was an attack made by measurement theorists who had grown out of physics, an attack on measurement in psychology, claiming that because of the lack of concatenation operations and so of extensive structures, that measurement was not really feasible in psychology. The developments of conjoint measurement, in the opinion of many people, belie that charge on the part of particularly the philosopher and physicist Campbell. All right, let us now turn to a formal discussion of what's involved in the theory of conjoint measurement. We're going to begin in the simplest case with a two-factor structure. So I'm going to assume that I have two sets of factors that are involved, A1 and A2, and the elements that one is dealing with are pairs, one chosen from A1 and the other chosen from A2, and I will write those pairs simply as a juxtaposition of symbols such as A and P, where A is from A1 and P is from A2. I'll use the early part of the alphabet for the first component and the latter part of the alphabet for the second. And there's a binary relation, again written as a curvy inequality. This binary relation is defined on the Cartesian product A1 cross A2. Now, at first blush, this looks simply like ordinal measurement. After all, the Cartesian product is itself a set, and you have an ordering on it, and that's all you have. And that sounds just like ordinal measurement. However, if you ask that the numerical representation do more than preserve the order, but also preserve, in some sense, the factorial structure, then this is not as simple as ordinal measurement. The fact that you're imposing factorial structure and trying to preserve that in some fashion will constrain appreciably the classes of scales that are involved. We'll talk about a representation of such a conjoint structure as decomposable if it's of the following character, that there is a function phi phi1 from A1 and phi2 from A2 into the reals. Two different functions, one on each component. And a function that has as its arguments pairs of real numbers and maps into the reals, capital F, and I'll assume that it is strictly monotonic strictly monotonic in each of the variables. Then we'll say this constitutes a decomposable representation if for every A and B in A1 and P and Q in A2, the ordering AP is greater than or equal to BQ holds qualitatively if and only if the composition of phi of A1, the scale value associated with A1, combined through the function f with the scale value associated with P, is greater than or equal numerically to the scale value of B1 combined through f with the scale value of Q. Now, not everything you can think of is a decomposable representation. This is a very general class of representations, and we'll be specializing it very appreciably in a minute. But let me point out that there are interesting representations that are not decomposable. Perhaps the simplest one to think about is this, where I have two scales on each of the components, phi1 and psi1 on the first component, phi2 and psi2 on the second component, and I assume that the phis and the psis are not the same functions. Then if I had a representation that associated with each pair, AP, the phi1 value of A plus the phi2 value of P plus the product now of the psi values of A and P. That is not a decomposable representation. One cannot put that in the form of a function of just two functions, one on each component. Now, if one has a decomposable representation, and all of classical physics tends to be of this character. I think a physicist feels that he understands the structure of what's involved, provided he can put it in a decomposable form. That is, he can understand the contribution of the first component and the second component to the resultant dependent variable. If that is true, if it is decomposable, then there is a very nice simple property that holds in the qualitative structure, and it's called independence. And it says the following, that if I look at an inequality in which the same second component holds, A and B are different, but the P is the same in the second component, then it doesn't matter what common value from the second component I put there. That the inequality will remain in the same direction if I replace the P in both places by the same element, say Q. That's the independence of the first component from the value in the second component, and the second line here describes the independence of the second component from the value in the first component. A is the same in both sides of the inequality, and if independence holds, it means that I can replace the A by any B and not change the direction of the inequality. And that is a consequence of the conjoint structure having a decomposable representation. It's a very important property because it permits us to induce on each of the components an ordering. In particular, on the first component, I will induce the ordering that I call qualitative greater than or equal to, or indifference to rather, sub 1 for the first component. That holds if and only if the inequality in the original conjoint structure holds in that direction with the same value in both components. And what the independence property does is say that this isn't going to change if I change the common value. This inequality will always remain the same, and so this definition is well defined. Similarly, in the second component, I define the inequality sub 2 if and only if the relation in the conjoint structure is in that direction with a common value A in the first component, and again by the property of independence. It doesn't matter what value I choose for A. So I will from here on out be assuming independence holds, and therefore that there is an ordering induced on each component, and this ordering will play a very important role. I haven't put it down explicitly on the blackboard, but let me mention it, that if independence holds, and if this is a weak ordering, which of course it must be if you have a numerical representation, then these induced orders are also weak orders. And that fact will be used repeatedly. Now, the case that we're going to be looking at for the rest of this lecture, the decomposition will be the additive one. That is, the function f of x and y will simply be x plus y. And I'll choose to write it in additive form rather than multiplicative form as the physicists do. And perhaps I should take a moment to do an aside on this. By taking exponentials, so that I look at the exponential of f of x and y, which is, of course, e to the x plus y, and that's equal to e to the x times e to the y, I can change the additive representation always into a multiplicative one, but notice that these now are positive variables, whereas I have made no assumption in discussing the additive case here that I'm dealing with positive variables. They may very well be negative. These are indistinguishable. A general additive case and a multiplicative case involving positive variables are the same structure from the measurement theoretic point of view. On the other hand, there is another kind of multiplicative structure that is not reducible to the additive form, and it's in some sense inherently multiplicative, and that is where the variables x and y can be both positive and negative. Then one cannot take logarithms to get into the additive case, and we reserve in the theory of measurement the name multiplicative conjoint structure to ones in which the multiplicative representation is into the reals, not just the positive reals. If we're in the case where we're in the positive reals in multiplicative, we conventionally call that additive, even though the physicists always write it in the multiplicative fashion. Now, when we get in this additive context, there are a number of necessary conditions that we can arrive at for the qualitative ordering from very simple properties of additivity and inequality. And let me go through one of these in a little detail and then point out that others follow in the same fashion. The one I will talk about in detail is known as double cancellation, and it makes the following assertion. It says that if you have a pair AX qualitatively at least as large as FQ and FP qualitatively at least as large as BX, and notice something now, there's a pattern here. There's an X here, and there's an X there, there's an F here, and there's an F there. The conclusion is that AP is qualitatively at least as large as BQ. Now that's a necessary property of the structure if it has an additive representation, as can be seen in the following way. If there is an additive representation, then this inequality goes into this numerical inequality. This qualitative inequality goes into this numerical inequality. Now, in the numerical domain, I can simply add these two inequalities. They're in the same direction, and that won't change the direction. So I just add all of these four terms and add all of those four terms. But then I notice, because of the way I've located the x's and the f's, there's a cancellation that can occur. This is found here, and it's found there, so we cancel them. and the F is found here and here. So they cancel, leaving over this pair being greater than or equal to this pair. And that corresponds, given that we're dealing with a numerical representation, so that it's an if and only if statement, that implies this condition. So that this property, known as double cancellation, is forced whenever you have an additive representation. The special case of this, when you're dealing with indifferences in these two inequalities, and the conclusion involves indifference, which you can see the indifference means you have the inequalities this way, and then you have the inequalities the other way, so that if you have just the indifference here, it forces the indifference there. That is known in the literature as the Thomson condition, and that is easy to graph to see what it means, and I've started the graph here. Let me think of the first component as lying along this dimension and the second component along this dimension. Then the first equivalence, in the case of the Thomson condition, says that the pair AX, here's A and here's X, so it's that point, and the pair FQ, here, this point, it's saying they lie on an indifference curve. That is, they're indifferent to one another, and there are various other points that are indifferent to them, and so you generate a curve called an indifference curve. Similarly, the second equation says the pair FP is on this point, and that's indifferent to the pair BX, which is on this point, and so they're on an indifference curve. Now the conclusion is that the pair AP, so I go from A on up to P, and I'll mark that as a square point, and the pair BQ, that's B here, and the Q comes over here, that produces a square point. The assertion is that they, too, lie on an indifference curve, that the structure of indifference curves is very strongly constrained in that fashion. Another necessary property, if you have an additive representation, is known as triple cancellation. You see that the name double cancellation here means there are two antecedent inequalities. Triple cancellation means there are three antecedent inequalities. And notice again the pattern. I've got an X here, and I have it on the left over there, and here it's on the right. I've got a Y here on the right and the corresponding Y on the left. I have an F on the left and an F on the right, and a G on the right and a G on the left. And so in the additive representation, those are all going to cancel, and I'm left over with the A on the left and a P on the left and a B on the right and a Q on the right. So the conclusion is that if these antecedent inequalities hold, then this resultant inequality must hold. And similarly, if I have this for just indifference, it forces indifference here, and that is known as the Reidemeister condition. Now, you see the pattern of the game, and you can start asking some questions. First of all, I've listed double cancellation here. Is there any other version of double cancellation? Are there any other patterns of inequalities, of pair of inequalities leading to a third? And the answer is yes, there's one more, and that is transitivity. Transitivity would take the form, say, AP greater than or equal to FX, FX greater than or equal to BQ, and that implies AP greater than or equal to BQ. And notice it is a cancellation property. The F's cancel and the X's cancel because they're on opposite sides. We've, of course, have already assumed that in the weak ordering assumption, and there's no reason to put it in anew, but it is an example of another cancellation property involving two antecedents. Those are the only possibilities. Now, when we go to triple cancellations, this is one of them. There are two inherently different other possibilities that I'm not going to write down at the triple level. Now you can ask, suppose I go to level of 4 inequalities, and indeed you again can find patterns where they will do the canceling leading to a single inequality, and there are quite a few more quadruple cancellation properties, and as you increase the number of antecedent, the number of possible inequalities rises very rapidly. So that the assumption of additivity forces a very large number of necessary conditions of this property. Now, one of the issues in the theory is how many of these do we really need? Can we get along with only a few of them in some fashion and derive all of the others? Or do we have to, in fact, in some way, list all of the possible cancellation properties? It will turn out that if we deal with sufficiently dense structures, and I'll define what I mean by that shortly, structures that in a sense are infinite in character, we will be able to deal with very few of these cancellation properties. On the other hand, if one is dealing with finite structures, which will be covered in a different lecture, then one is forced to state in some fashion essentially all conceivable cancellation properties that none will, or very few will derive from the existence of the others. All right, now I need to worry about two more things before I can state the theorem, or a theorem, the first theorem about an additive representation. As you might expect, I have to deal with the Archimedean issue. And what we do is introduce again a concept of a standard sequence, a sequence of elements A sub I from the first component is said to be a standard sequence if and only if we can find two elements, P and Q, in the second component, and they've got to be chosen so they're not indifferent to each other in the induced order and on the second component. I want them to be distinct, one larger than the other. And it turns out, if I can find P and Q such that for all pairs of elements in the sequence, AN minus 1 and AN, they're successive elements in the sequence, and I don't want to state that there. The indifference ANQ indifferent to AN minus 1P obtains. Now, there's a certain way of graphing this that may give you an idea of what's involved here. Suppose I think of the two components as lines that are lined up parallel to one another. For some purposes, it's useful to make the graph as if it's orthogonal, but for this purpose, it's better to put them side by side. And now I have my P and Q on the second component. And what a standard sequence is a series on the first component, which intuitively has the property that the interval between successive ones over here exactly corresponds to the interval between P and Q. Now, the way we say that is that we combine, for instance, A1 with P and A2 with Q, and they just balance each other. They're just indifferent. And then we look at the A2, A3 one. We put A2 with P and A3 with Q, and again they just balance. And then when we go from the interval 3 to 4, we combine A4 with Q and A3 with P, and they just balance. A balance being shown as an intersection at the midpoint between the two lines. So that the standard sequence is, in some sense, a replica of intervals all equivalent to the same interval on the second component. It's our way of establishing a unit, well, not really, I'm sorry, not a unit. We're establishing a common interval growth on one component. There's a similar definition, of course, the other way, where we fix the two elements over here and build up the sequence of intervals on the right-hand component. And in the case of the additive structure that we're trying to get at, these intervals will turn out to actually have numerically the same values in the representation. They're essentially at multiples of one another and play just the same kind of role as the standard sequence did in the theory of extensive measurement. And our assertion of the Archimedean axiom will simply be that a bounded standard sequence is finite, where in this case, however, the standard sequence is not, has no starting point. It may go down toward minus infinity, so the bounds have to be given at both sides of the standard sequence, unlike the extensive measurement case. That, again, is a necessary property, and as always with the Archimedean property, it's fundamentally untestable using finite sets of data. The last two properties, one of them is relatively trivial, and let me just mention it here. It's an assertion that each factor makes a difference. That is, in the induced relation on each factor, there is at least one pair of elements that are where the strict inequality holds. And this is just to avoid certain triviality. The important strong constraint is what is called unrestricted solvability in the structure. And it states the following, that if I give you any three elements, two of them from one component and one from the other. So, for instance, suppose I give you A and B and I give you P. The assertion is then I can find a Q in the second component that will cause the indifference relation AP indifferent to BQ to hold. Or if I give you P and Q and B, I can find A in the first component to make it hold. This is a very strong property. It's one that in many of the physical examples one would be willing to assume it. In certain psychological examples, it isn't really true. For instance, let me give one familiar example. If I look at loudness contours, so I plot log frequency versus log intensity, the loudness contours are approximately of the following character. Equal loudness contours are something of this character, and there's a region in which you can hear, and outside that region you cannot hear. Now, suppose I give a particular point, let's say here, that's a particular intensity and frequency, and now I want to pick another, let us say, intensity. Suppose I pick this intensity. Then that cuts through the plane here, and I cannot find any frequency that will cause that intensity to be indifferent to this particular sound of this intensity and frequency. Now, if you kind of imagine that this outside the range of hearing, these curves continued on, of course, then you could find such a point, for example, right there. But in terms of what is observable empirically, the solvability condition is not met in that example. So that the theory that I'm talking about at the moment is extremely restricted. It would not apply to this case of loudness. On the other hand, it will apply to many cases in physics. Now, it turns out that we have enough concepts about the qualitative conjoint structure in order to establish the theorem. The theorem that I will state here, the first theorem that was proved, and in many ways the simplest theorem, is due to de Broglie, who proved it under some slightly different assumptions that involve topological assumptions, and a little bit later Luce and Tukey proved it in the form that is stated here. And the assumptions are that the ordering is a weak order, that double cancellation holds, you recall that property, that unrestricted solvability holds, and that the Archimedean property holds. Now, you're probably a little surprised that I haven't put in independence, because independence was the first and, in a certain sense, the most important property. It's not put in because from unrestricted solvability, weak order, and double cancellation, one can immediately prove independence. And so you first put in these properties and then derive independence, and I'll do that in a moment. And then that makes the Archimedean property make sense in that we now assume every strictly bounded standard sequence is finite. And the conclusion, the representation conclusion, is that there is an additive representation of the conjoint structure under these assumptions. The uniqueness of this representation is stated here. If we have phi1 and phi2 as one additive representation and phi1 prime, phi2 prime as a second one, then the assertion is that there exist three constants. Alpha is a positive one, and beta 1 and beta 2, which may be positive or negative, such that for all elements in the system, phi I prime is alpha phi I plus beta I. That is, there is a linear relationship, positive linear relationship between phi I prime and phi I. Note, however, that while the additive term, which controls the zero of the scale, is independent for the two scales, the first and the second one, the unit of it, which is represented by this coefficient, is the same for both. There's a common unit. And these are spoken of as interval scales with a common unit. This is not quite as strong a uniqueness result as we had in extensive measurement. Remember, there, scales were related simply by a multiplicative positive constant. Here we have an added free term, so that essentially, instead of having only one element of indeterminacy as in extensive measurement, here there are two elements of indeterminacy in the scale, usually referred to as the zero and the unit of the scale. If we were to have cast the representation in multiplicative rather than additive form, then the uniqueness would have taken this character. If the size or multiplicative system of scales, then they would be related to each other by a power transformation where gamma and alpha are both positive constants. And one refers to that kind of uniqueness result as a log interval scale, the essential meaning being that if you took the logarithm of these representations, you would end up with an interval scale. Now, the proof of this theorem is comparatively simple, and I'll sketch it fairly fully. The original proof that Tukey and I gave is rather hard to follow and has since been much simplified. The first major step in simplification was due to Krantz, who showed one way that you can use Holder's theorem to prove the result, and then later Holman suggested the idea that we will use in the present proof. The first step in the proof is to establish that independence in fact holds, and that is very easy. I suppose AP is greater than or equal to BP. Then by the solvability condition, I can find an element C such that BQ is indifferent to CP. Now notice that this is common here, and the B is common here, so double cancellation applies. This gives me AQ greater than or equivalent to CP, but CP was indifferent to BQ, and then using the transitivity of the ordering relation, we conclude AQ is greater than or equal to BQ, which is the property of independence for the first component. A completely analogous proof gives it on the second component. Now we go to the important step of the important idea of proof, and that is to induce an operation on the first component. And we do that as follows. We choose arbitrarily an element A0 of the first component and an element T0 of the second component, You can intuitively think of these as a choice of what's going to be 0 in the system, in the representation. And we define a function from the first component to the second component that I'll call pi, and the operation O1 that is a function mapping the Cartesian product into the first component. These are defined as the solutions to the following equations, which by unrestricted solvability we know exists. The pi is selected to be that element of the second component which solves the equation AP0 is equivalent to A0 pi of A. In this diagram, what we're doing, for instance, if we wanted to solve for A, we're finding the element over here on the second component, pi of A, such that this combination is balanced by that combination. The second solution is to take A combined with pi of B on this side, put P0 on this side, and solve for this unknown here, and we will call that A01B. And on the diagram, let's see what we mean. First of all, we found pi of B. That's an element over here. Here's A, and here's B. And what we're intuitively trying to do is the following. We want to take this interval, the interval from A0 to B, and tack it on top of A, and to get the point up here that we're going to call A01B. And the way we're doing it is first we reflect B over into the second coordinate so that this interval is essentially the same in the second coordinate as the interval from A0 to B. And then we look for the interval in the first coordinate, which coupled with this, P0, is indifferent to A coupled with pi of B. And that is a way then of essentially taking the interval from A0 to B and shifting it up so that it now lies from A to wherever it goes, and we're calling that A0 sub 1 B. Now, the next stage of the proof is to take the structure A1, the induced ordering sub 1, and the operation O1, factor out the equivalence relation and work with the equivalence classes, and prove that that structure is an Archimedean ordered group. Well, it's trivial that since the induced ordering is a weak order, then factoring out the indifference relation produces a simple order. The element A0 will serve as an identity in this structure. We can see this as follows. We note that by the definition of pi, A0 P0 is indifferent to A0 pi of A0, which forces pi of A0 to be the same as P0 in the second coordinate, so that we've mapped in the pi relation A0 maps into P0. And now if I look at A concatenated with A0 and P0 in the second coordinate, I can replace the P0 in the second coordinate by pi of A0, and that, what I'm doing in the first line here is using the definition of O1, which says that we take the first element before the O1 and put it in the first coordinate, and the B from the second position becomes the pi. So here in the second position is the A0. That puts the pi of A0 here. And then we use the fact that pi of A0 is the same as P0. And then by independence, that means that in the first coordinate, this must be equal to that, which is the property of the identity. You have to, of course, do it the other way, and it's easy to do. We define an inverse to be the solution to the following system of equations. We essentially find on the second coordinate the value that coupled with A on the first coordinate ends us up at the A0 P0 point, and we then put that zeta of A in the second coordinate and define the solution to this equation, the element in the first coordinate we'll call the inverse of A0. We note that pi of A inverse is equivalent to zeta of A. And then it's a simple verification that this does in fact behave as an inverse. It's a very simple calculation. To show that the concatenation operation is associative, we first use the definition of pi and double cancellation to prove that you can always interchange the A and a B in an expression of the form A pi B. It is equivalent to saying B pi of A. And I'll be using that in a second. Now, I observed that A0B, 1 here, is by definition this quantity, and B0 sub 1 of C is by definition this quantity. And notice I can use double cancellation because the B's are in common here and the P0s are common here, and that gives me this expression, which I'll hold on to for a second. And now I'm ready to work with associativity. So I look at the element A0 concatenated with these I'm forgetting the ones on the O's here. Better stick them all in. So I've got A0 concatenated with B concatenated with C1, and that is by definition of this O0 term equal to A comma pi of B O sub 1C. And now I use the fact that I can invert them. I can interchange what's here and here just like that. I've already proved that. And then I get from this to here using what I proved here. I know that BOC pi of A is AOB pi of C. That gives me this. And that then by the definition of O1 yields this. And then by independence, this is common term here, so by definition this has to be equivalent in the first coordinate to that. The monotonicity follows very simply. If I begin with A at least as great as B, then I can put by the independence property a common value, which I'll choose to be pi of C in the second component. That then by definition is AO1 of C and BO1 of C on the right-hand side with a common P0, and using independence, that yields the property that we want for monotonicity. Of course, you have to do the other side, but it's essentially the same proof. I won't give the proof that the Archimedean property holds, but you can see that it's been built into the axiom so that it's very easy to prove it. Then I use Holder's theorem. I know there's an additive representation, which I'll call phi1, of this Archimedean ordered group that I've constructed on the first component. And I can define phi2 in terms of phi1 using the operation pi, which converts pi takes an element of the first coordinate and maps it into an equivalent one on the second coordinate. If I take the inverse of that operation, then I go from the second coordinate back to the first coordinate. So I take my p, go back to the first coordinate, and compute phi1 of that value and define that to be phi2 of p. And now I'm ready to prove that the sum phi1 plus phi2 is in fact an additive representation. Let me pick an A and B in A1 and a P and Q in A2 such that the inequality AP greater than or equal to BQ obtains qualitatively. And let me define the elements C and P to be those elements that map into P and Q respectively. So that inequality can be, we can replace the P by pi of C and the Q by pi of D. Then we know by definition of of O1 that this is equivalent to A O1 of C is greater than or equal in the first coordinate to B O1 of D. And that, by Holder's theorem, then has the property phi1 AO1C is greater than or equal to phi1 BO1D. But Holder's theorem not only says that it exists, it says that it's additive, so that's equivalent to this statement using the additivity of the operation of the representation of the operation O1. But now C is replaced by pi inverse of P, and D is replaced by pi inverse of Q, and that, of course, is what we've defined to be phi2 of P, and this is phi2 of Q. We substitute that, and there's the additive representation. The uniqueness of this representation follows almost directly from the uniqueness of Holder's theorem, but I won't work out the details. It's a very easy matter to prove it. So that the essence of the proof idea is to map what amounts to the Cartesian structure under the relation, to map that into an operation on the first component. The Cartesian product coupled with the relation on it is being reflected entirely in this first component through this operation O1. And the fact that it can be then shown to be an Archimedean ordered group permits us to use the result we already had to perform the construction. Now, this is a very simple result and easy to remember, but it does suffer from the fact that it is fairly restricted and cannot be applied in certain situations. The reason for the restrictiveness comes not from any of the necessary properties, the weak order double cancellation, and Archimedean can't be the source of the problem. If you're going to have an additive representation, they've got to hold, but it comes from the unrestricted solvability. That's a very strong condition, and the question immediately arises, can we weaken that condition? We may be forced, if we do weaken it, to throw in some more necessary conditions. We cannot assume automatically that this could be weakened and leave everything else the same. Now, the form of weakening that has been explored in the literature, really there are two forms of it, and I'm going to talk about one of them in this lecture. The other form is to consider structures that are finite and in which really no solvability is postulated at all. And those will be dealt with in a separate lecture. In this lecture, I'm going to continue to work with structures that have an enormous amount of richness, but I'm not going to require that all equations be solved. Rather, the condition is as follows. Suppose that I have in the structure an inequality of this form. Now let's notice what the pattern is. There's the element AP is here, and I've got a common Q here on the second coordinate, and there's an element in the first coordinate that causes, when combined with Q, isn't as large as the AP value, and another element that I'm calling B upper in the first coordinate, which when combined with Q, at least is as large as AP. And the assertion is that whenever that obtains, then there exists somewhere between B upper and B lower an element B that causes an exact solution. And there's a similar property on the second component. I won't write it explicitly, but it's a complete analog of that property. Now you see, what this property is saying is that, well, there may be circumstances in which you can't find the solution because you can't find something that's above it and something that's below it with Q in the second coordinate. But if you can ever get in that position of bounding the AP term, then we're essentially saying that things are sufficiently continuous in the first coordinate that we can find an element that brings the B star down just to the point where it causes indifference with the AP term. With that concept of solvability, the theorem is changed only slightly. We, of course, assume weak order. We now explicitly assume independence. We didn't need to do that before because that was the independence axiom was not independent of the other axioms. It could be derived from them. Instead of double cancellation, we put in the somewhat weaker condition, the Thomson condition. That is, double cancellation holding only for indifference relation. We have restricted solvability. The Archimedean property is unchanged. We assume that each of the components is essential. We're avoiding trivialities. The conclusion is the same, that under those circumstances, an interval scale additive representation exists. Now, the proof of that theorem, which is a more useful theorem than the Luce-Tukey theorem, the proof of this is really quite a bit more difficult. The ideas are basically the same, and the reason that I gave the proof in some detail for unrestricted solvability is because very nearly the same ideas are involved here, but the details of carrying it out are vastly more complicated. One, again, induces an operation on the first component. Well, that's not. I'm not being quite accurate about that. Let me indicate exactly how one proceeds. I'll sketch it graphically. Let this be the first component and this the second component. I will find elements, call them A lower and A upper, and P upper and P lower, such that A lower with P upper is indifferent to A upper with P lower. And you have to show that you can find such elements. And then I'll work with this little subsystem in here and use essentially the same construction as we used in the proof of the case of unrestricted solvability to construct an operation. However, it will turn out to be a partial operation, not a closed operation, and one has to then use the theory of extensive measurement for partial operations to carry out the construction of the representation of this operation in the one coordinate. Having done that, one then has to extend this system that you now have for this subpiece to the rest of the structure. And basically one does a mapping operation that takes any points in here and moves them down into this structure in a very systematic fashion and essentially reduces the problem from wherever you are beginning to an analogous point move down here, but you count the number of steps that were involved, and this permits you to carry out a very systematic construction. In that stepping operation, one has to use the triple cancellation property, and one of the parts of the proof that takes a fair amount of time is to show that from the assumptions here you can derive the triple cancellation property and then make use of it in constructing the proof. This is all worked out in considerable detail in the Foundations of Measurement.